This is the continuation of EE5508 optical processes in semiconductors. Today we'll discuss the direct and indirect transition in semiconductors. This shows the band structure of a direct band gap semiconductors plotted as energy as a function of wave vector k. From the top valence band to the bottom of the conduction band, we define this as the band gap energy. If we come in with a photon energy of h bar omega and excite the electron near the top of valence band to near the bottom of the conduction band. So you will leave a hole behind and the electron will stay near the bottom of the conduction band. The top of the valence band we define as the energy equals to 0. That is taken as the reference point. So from here to the bottom of conduction band, that is the kinetic energy of the electron, which is equals to h bar squared k squared over 2 me star, where me star is the electron effective mass. Measure from the top of the valence band downwards is the EI, which is the initial energy, and therefore is equals to h bar squared k squared over 2 mh star, where mh is the whole effective mass. So the final energy, okay, measured from the top of the valence band will be Eg plus the kinetic energy. For the initial energy, you measure downwards from the top of the valence band, is negative value, so it's minus h bar squared k squared over 2 mh star. By conservation of momentum, initial momentum of the electron plus the photon momentum is equals to the final momentum of the electron. So Ki, Kf are the initial and final wave vector of the electron, and Q is the wave vector of the photon. So h bar q is the momentum of the photon. Now, h bar q, the photon momentum, is much less than the electron momentum. And Kf is basically equals to Ki is equals to K, because this is just a vertical transition and occur at the same K value. So initial K equals to final K. Now, why the photon momentum is much less than the electron momentum? The momentum of a photon is h bar over lambda. The lambda is the wavelength of light and is usually in the range of 10 to the power of 3 to the 10 to the power of 4 Armstrong. And that gives you a h bar omega of about a few eV. The momentum of electron is h over a, where a is the lattice constant. And the lattice constant of the crystal structure, for example, is about 5 Armstrong. So therefore, if you plug in this value, you will realize that the photon momentum is much less than the electron momentum value. Equation 2.3.12, which is this equation, where Kf equals to Ki equals to K, basically state that it's only a vertical transition between the valence band and the conduction band, which are allowed if only photons are involved in the transition. So this is a vertical transition and it's the same K value. So initial K equals to the final K. And I mentioned again measure from the bottom of conduction band to where the electron is, this is the kinetic energy, or we call that the electron energy. And measure from the top of valence band, since we take the top of valence band, reference energy equals to 0, you measure downward is negative value. So this is the whole energy. Now, if we take equation 2.3.9 minus equation 2.3.10, which is this equation minus this equation, you will have EF minus EI. And then you have this EG plus H bar squared, K squared over 2 ME star, minus H bar squared, K squared over 2 MH star. You can factor out the H bar squared, K squared over 2, you will get this part of the value. And then the 1 over ME star plus 1 over MH star, we define this as the reduced mass. So 1 over MR star, the MR star is the reduced mass, is equals to 1 over ME star plus 1 over MH star. And you can calculate the reduced mass. Now, EF minus EI, final energy minus initial energy. By conservation of energy, EF minus EI give you the H bar omega, which is the photon energy. So this is the photon energy. And then you will have EG plus H bar squared over 2. And then this one, the whole term is called the 1 over MR star. So the conservation of energy will give you H bar omega equals to the band gap plus H bar squared over 2 MR star. Now, we will introduce the density of state in 3D. I suppose you have studied this in Prof. Wu's course. The density of state, okay, as a function of K is defined as follows. To obtain the joint density of state, because you are exciting the electron from the valence band to the conduction band, so you involve the density of state in the valence band and the density of state in the conduction band. So you must have available number of electron in the initial state, which is the valence band, and then you will also involve the empty state or the available empty state in the conduction band. And therefore, we involve valence band and conduction band. We call this the joint density of state. So, how to convert the density of state as a function of K to the density of state as a function of energy? From here, you can differentiate the photon energy with respect to K. Okay, and then you substitute the K and dK, because this one you differentiate d H bar omega over dK. So you will have a dK here in this equation, and then you can plug it inside. So I'll leave it to you to do the mathematics, and this gives you the density of state, or the joint density of state of the conduction band and valence band. Now, let us look at one example. A photon energy of 2.2 eV is absorbed by a valence band in gallium arsenide. If the band gap of the gallium arsenide is 1.43 eV, calculate the energy of the electron and hole produced by this photon absorption. Given the electron effective mass and hole effective mass of gallium arsenide is 0.067 m0, where m0 is a free electron mass, and 0.45 m0, which is the whole mass, and then calculate the wave vector k measured from the conduction band minimum. So if you look at this diagram, you're coming in with photon energy, okay, not much larger than the band gap. So you expect to be able to excite the electron near the top valence band to near the bottom of the conduction band. We are supposed to calculate this electron energy and this hole energy. Now, effective mass and whole effective mass are given to you. So in principle, if you know the K value, you should be able to calculate the electron energy and the hole energy. In this question, the wave vector K is not given to you. So, how to approach this problem? Using the conservation of energy, H bar equals to band gap plus H bar squared K squared over 2 MR star. You divide both sides by MR star over ME star. So you bring the EG over, will be H bar minus EG, and then you divide both sides by MR star over ME star, or we say that we multiply by a factor of MR star over ME star. Then you'll get H bar squared K squared over 2 ME star on the right hand side. And this is actually the electron energy. So from the left hand side, MR star, you can calculate the reduced mass. Electron effective mass is given to you. H bar omega is 2.2, band gap is 1.43. So again, you get the electron energy of 0.667 eV. Similarly, for hole energy, you multiply both sides for this equation by a factor of MR star of MH star. You will get the hole energy, okay, to be of this value. So you can plug in the reduced mass and the whole effective mass, for the photon energy, and the band gap. You'll get 0.099 eV. So in terms of magnitude, it's 0.099 eV. So without knowing the K value, you can find the kinetic energy of the electron and also the whole energy in the valence band. How do we calculate the wave vector measured from the conduction band minimum? So refer to this diagram again. So there's some value of K, which is Ki equals to Kf equals to K. So the electron is at this value K and measured from the bottom of the conduction band. The bottom of the conduction band occurs at K at the gamma point. So let us look at this diagram in the next slide. So this is the K value I'm talking about. This is the top valence band, which is the gamma point. Actually, if we already calculated the electron energy to be H bar squared K squared over 2 ME star, the electron energy is 0.667 eV. You multiply by 1.6 times 10 to the power minus 19 to convert it to joules. H bar squared is H over 2 pi, Planck constant divided by 2 pi. You'll get a value of 1.055 times 10 to the power minus 34 joules second. So all in SI unit. K is the value that I want to find. The electron effective mass is 0.067 times m naught. M naught is a free electron mass. It's 9.11 times 10 to the power minus 31 kilogram. So you will get K value in the SI unit of per meter, which is about 10.8 times 10 to the power of 9 per meter. Now, let us look at the band diagram again. At the conduction band minimum, which is down here, which is also occur at the top of valence band, this is the gamma point. The gamma point is at Kx equals to 0, Ky equals 0, Kz equals 0, 3 components. And the unit is 2 pi over A, where A is the lattice constant. For the current question, the electron is at some k value. So electron occur at some k value, which is this k, which is this k. So in principle, if you know the k, which is kx, ky, kz, and measure in 2 pi over a, then if you take the modulus k, you can find the k value. So that gives you the square root of kx squared plus ky squared plus kz squared, 2 pi over a. That's how you find the k value. But in this question, since kx, ky, kz is not given to you, you can calculate from the electron energy. Next, we would like to discuss the indirect transition for an indirect bandgap semiconductor. And for indirect transition, it involves phonons. So this session, we have to review a bit of phonon scattering. And you have studied this in Prof's course. So I take these slides from Prof. Wee Hong. Okay, this example basically show the lattice dispersion curve of a silicon. Okay, frequency, phonon frequency, okay, not photon, phonon frequency is a function of the wave vector beta. So I use beta here as a phonon wave vector to differentiate from the electron wave vector k. Okay, beta for phonon wave vector. In silicon, you have 3 acoustic branch, 1 longitudinal acoustic, and 2 transverse acoustic mode. And you have 3 optical branches, 1 longitudinal optical, and 2 transverse optical mode. Note that the dispersion curve, of course, is dependent on the crystal orientation, and also the lattice vibration depends on the crystal symmetry and atomic spacing along a particular crystal direction. So for this course, we will focus basically at the gamma point, okay, to find out more of the phonon scattering based on this frequency. So if you look at the gamma point, this portion is more of the acoustic branch, longitudinal acoustic and transverse acoustic. So near beta equals to 0, okay, this is approximately linear dependence on beta for the frequency. At beta equals to, near beta equals 0, you look at your longitudinal acoustic and transverse acoustic. Okay, here is almost flat. Okay, so we approximate, okay, the acoustic mode. Okay, basically this is the expansion of this curve and the expansion part of this curve. So this part, okay, is linearly dependent for the phonon frequency as a function of beta for the acoustic mode. And omega is the angular frequency. So acoustic is related to sound. So Vs is the sound velocity. The phonon wave vector give you the angular frequency of the acoustic mode. Near beta equals to 0 for the optical branches, you can see that they almost flat, constant value. So we take this as a constant value, okay, omega equals to omega naught. So omega naught represent the angular frequency for the optical mode. Different semiconductors will have different optical phonon energy and also different acoustic phonon energy, because different semiconductors, they have different phonon dispersion curve, because different semiconductors, they have different structures, and they depends on the crystal orientation, and they depend on the crystal symmetry. Now, let us make some sense, okay, of this frequency near beta equals to 0 for acoustic branches and also the optical branches. Given sound velocity is 340 meter per second, what is the acoustic wave vector for a frequency of 1 times 10 to the power of 12 Hertz in silicon? So down here, back in this diagram, near beta equals 0, let's say about 1 times 10 to the power of 12 Hertz. Okay? And the sound velocity is given to you. So the angular frequency, okay, is 1 times 10 to the power of 12 Hertz. What is the acoustic wave vector? So at low frequency, which is about 1 times 10 to the power of 12 Hertz in silicon, which is your transverse acoustic phonon, omega A is given to you as 1 times 10 to the power of 12 Hertz. Omega is velocity times beta. So the velocity is equal to omega over beta. Omega is 2 pi mu, which is the frequency over beta. So you can rearrange the term. Beta will be equal to 2 pi mu over the velocity of the sound. So the frequency itself, okay, is 1 times 10 to the power of 12 divided by the sound velocity. That gives you 1.5 times 10 to the power of 10 per meter. Now, there's a mistake down here because omega A, in principle, it should be the velocity V. So let us make a correction here. This is the velocity. So if we look at the plot of the diagram, okay, this was plotted as a frequency mu. So 1 times 10 to the power of 12, which is the frequency. Some textbook will plot as omega, but omega is just 2 pi mu, just a factor of 2 pi. So for our analytical calculation, to be exact, okay, based on this graph, is frequency. So the frequency is 1 times 10 to the power of 12. So this should be the frequency and not omega. Now, calculate the acoustic phonon energy for beta obtained in 1. You already obtained beta value. Beta value is 1.8 times 10 to the power of 10. So omega A is actually h mu because h bar is h over 2 pi. Omega is 2 pi mu. So 2 pi in the numerator and denominator will cancel off. You're left h mu. H is the Planck constant, 6.26 times 10 to the power minus 34, times the frequency, which is this one, and then divide by 1.6 times 10 to the power minus 19, because I want to convert this into EV. So I get 4.14 times 10 to the power minus 3 EV, which is about 4 MeV. So you can see that the acoustic phonon energy is very small. It's a few MeV. Now, let us calculate the optical phonon energy at the frequency of 15 times 10 to the power of 12. So if we look at the optical frequency, okay, at the beta equals to 0, at this frequency is about 1 times 10, 15 times 10 to the power of 12. So same thing, h bar omega is h mu, Planck constant times the frequency of the optical phonon divided by 1.6 times 10 to the power minus 19 joules, give me about 60 MeV. So in silicon, near beta equals 0, the optical phonon energy is 60 MeV. So this is the characteristic of the optical phonon energy in silicon. If you have another phonon dispersion curve for gallium arsenide, the optical phonon energy will be different. It's about 36 MeV. Now, scattering of mobile carriers in semiconductors. And this has been introduced in 12th course. Imagine that you have an electron moving inside a semiconductor crystal, and your semiconductor crystal all arranged periodically for the lattice, or the atoms are arranged in a periodic potential. So as your electron travel inside the semiconductors, it will be scattered by all these lattice vibration, or we can say that the atoms is vibrating at equilibrium position. So we call that the lattice vibration. So electron will have to interact with all these lattice vibration and get scattered. So electron and the lattice vibration, sometimes we call that the phonon. So electron and phonon will interact. So this is called an electron-phonon interaction. So when they interact, they will exchange momentum, they will exchange energy. So electron can emit energy to the surrounding, which is your lattice or your atoms vibrating at equilibrium position, or they can absorb energy from the surrounding, which is from your atoms or your lattice. Now, that is assuming there's no other scattering mechanism. For example, there's no defect scattering, there's no carrier-carrier scattering, so you have only lattice scattering, and your atoms are arranged periodically, okay, in the crystal, so you have only lattice scattering. So you have intra-valley, which is scattering within the same valley, or inter-valley, which is scattering from one valley to another valley. Let's say from the gamma valley to the L valley, or from the L valley to the X valley. Both intra-valley and inter-valley can involve acoustic or optical modes. Okay, and therefore you need to know the acoustic and optical phonon energy based on the phonon dispersion curve. Apart from the lattice scattering, if the carrier is heavily doped, then you can have carrier-carrier scattering. So there are many electrons in the crystal potential. The electron and the electron will interact in the world, and this we call that the carrier-carrier scattering. If you have defect in semiconductors, okay, some of these defects are not shallow impurity. It could be also deep impurity, which gives rise to crystal defect. Or you can even have alloy, which is instead of gallium arsenide, you have ternary alloy, aluminum gallium arsenide, and such mixture of the element can also give rise to scattering effect. Now, I want to establish the fact that acoustic phonon is elastic scattering and optical phonon is inelastic scattering. Remember, energy and momentum is conserved between the electron and phonon. Since electron traveling inside the crystal will interact with the phonon, or sometimes we call that the lattice vibration, before and after scattering. So in acoustic phonon scattering, is actually elastic because near the wave vector equals 0, the frequency is small, approximately equals to 0. So if you come in with an electron, it interact with the phonon, so the electron will have initial energy and initial momentum, which are just K, and the phonon energy, EP, P stands for phonon, and the initial phonon wave vector. And after they interact, let's say the electron scattered, you have a final electron energy and final momentum of the electron. Similarly for phonon, final phonon energy, final phonon wave vector or momentum. So by conservation, initial electron energy plus initial phonon energy will be equals to final electron energy plus final phonon energy. And similarly for the wave vector or the momentum, h bar k, electron initial momentum, h bar beta initial phonon momentum, final electron momentum, and final phonon momentum. For acoustic scattering, near beta close to zero, oscillate the frequency or the angular frequency to be zero. So you can see that the phonon energy is h bar omega. So this term and this term goes to zero. Initial of the electron equals to final energy of the electron. Okay, and beta is near zero, so we can also drop h bar beta I and h bar beta for the final phonon wave vector or the momentum. So you have h bar and h bar cancel off, you have ki equals to kf. So this basically established that the acoustic phonon that scattered the electron, okay, basically the scattering is elastic. Now, for scattering by optical phonon, okay, is inelastic. The energy of the electron can decrease or increase after scattering. So when a phonon is either created, we call that the generation of phonon. That is emission of phonon. When the phonon is absorbed by the electron during the scattering, we call that the annihilation of the phonon, or the phonon is destroyed. So let us look at this diagram. Okay, I forgot to mention that such a diagram is called the Feynman diagram. The incoming electron, okay, traveling inside a semiconductor, absorb a phonon and then scattered. And this gives you the final energy of the electron and final momentum of the electron. So you can establish initial electron energy plus a phonon energy, electron absorb a phonon energy, and that gives you the final electron energy. Momentum the same, initial momentum plus the initial momentum of the phonon equals to the final momentum of the phonon. I just dropped the h bar because h bar will cancel off. Now, instead of absorbing a phonon, let's say electron travel inside the semiconductors, it can emit energy to the lattice. Such an emission we call emitting of phonons, and then electrons get scattered. So initial electron is equals to the final energy of the electron plus the final phonon energy, or the emission of phonon energy. And similarly for momentum, initial momentum equals to the final momentum of the electron plus the final momentum of the phonon. So you can see that, okay, the energy of the electron, okay, is either increase or decrease, and is known as inelastic scattering. So by absorbing a phonon, okay, is considered as inelastic scattering. Emission of phonon is also inelastic scattering because the energy of the electron after scattering is increased because it absorbs the phonon energy, or decrease because EI minus EF, that is emission of phonon energy. So the energy of the electron in the final state is decreased. Now, with that, we can study the indirect transition between indirect valleys because such a transition will need to involve phonon energy. Let us look at this band diagram. Energy as a function of K, and this is the top of valence band, and the minimum of the conduction band, let's say, occur at some point of K. So for example, in germanium, it will occur at the 111 value. Now, these are the bottom of the conduction band. This is also the bottom of the conduction band. But the minimum of the conduction band occur down here. So, as long as your top of valence band and the minimum of conduction band does not occur at gamma point, this is an indirect band gap semiconductor. For direct band gap semiconductor, the conduction band, okay, should be lower than this, and the minimum will occur at the gamma point. Okay, and the same as the top of valence band. You have learned that in Prof. Wu's course. So how do we make a transition? Okay, let's say you come in with photon energy to excite the electron, let's say at the top of valence band to the conduction band minimum, let's say in germanium, the L value. There are two ways to do this. Okay, so this is the top of valence band, this is the minimum of conduction band, this is the indirect band gap, and this is a change in the wave vector because in direct band gap, there's no change in wave vector. Ki equals to Kf. That's the vertical transition. Now you're going from here to here. So there's some K value here respect to the gamma point. So there's a change in K. You can come in with a photon energy, excite the electron to a virtual state, but smaller than this indirect band gap energy. So your incoming photon energy is less than the indirect band gap energy. And then you absorb the phonon energy from the lattice and you make a transition to the bottom of the conduction band. Or you can come in with a photon energy, for absorption of phonon energy, that will be photon plus phonon give you the indirect band gap energy. Another way to do this is you can come in with a photon energy greater than this indirect band gap energy. So it goes to a virtual state by exciting the electron from the top of valence band to a virtual state. And then you make a transition to the bottom of the conduction band by emitting phonon energy to the lattice. So you write the equation omega, which is a photon energy, by emitting a phonon, so you minus the phonon energy is equals to the band gap energy of the indirect band gap semiconductors. So there are two-step process. And either way, we can make a transition. So let us look at the analysis for this indirect gap semiconductors. The transition of the electron from the top of valence band to the bottom of conduction band require a change in both energy and momentum. So as we discussed, it's a two-step process, either by absorption or by emission of photon, because the photon itself cannot provide the change in the momentum also. So the momentum is conserved through absorbing or emitting a photon. So it's either you can do it with transverse acoustic or transverse longitudinal acoustic or transverse optical photon with photon energy EP. Now, for absorption of photon, initial momentum of electron plus the initial momentum of the photon plus the photon wave vector equals to the final wave vector of the electron. For energy, initial energy of the electron plus the incoming photon energy, and then plus, because you absorb a photon, so plus a photon energy equals to the final energy of the electron. You rearrange the term, h bar plus EP will be equal to EF minus EI. Emission of photon, initial momentum of the electron plus the incoming photon momentum. Since you are emitting a photon minus the photon momentum equals to the final momentum. And then the energy, initial energy plus incoming photon energy, photon energy, since you are emitting, will give you the final energy of the electron. H bar omega minus EP will be equals to EF minus EI. So here, H bar omega plus EP equals to EF minus EI, final energy minus initial energy. So this plus EP means absorbing photon energy, is minus EP is the emission of photon energy. Now, in previous session, we said that the photon momentum is much less than the electron momentum. So we're going to drop the h bar cube here. Similarly, in this case, h bar cube is dropped. Now, we write EF since both equation, absorption of photon and emission of photon, involve EF, of course involve EI and EP. We write it elegantly as h bar omega minus plus EP plus EI. So the minus A basically for the absorption of emission of photon, and plus is for the absorption of photon. And momentum, since we drop the h bar cube, so you have also minus plus. Okay, so the minus is for the emission of photon, plus is for the absorption of photon. Now, next we want to derive the absorption coefficient. Similarly to the direct bandgap semiconductor, we have this absorption coefficient for direct bandgap semiconductor. Okay, goes like a square root dependent for the photon energy. So the absorption coefficient, okay, must involve the initial state or the initial density of state and the final density of state. So we need to know the product of the initial density of state and final density of state. So the density of state, okay, for the initial electron at the top of valence band is given as this value. You study in Prof's course for the density of state. Okay, so in the valence band, we involve the whole effective mass. Now, the density of state for the conduction band will be EF minus EG for the density of state. You can refer to this diagram again. This is the density of state at the valence band, which is EI or EF, and this is the density of state in the conduction band, and you have to overcome this band gap energy. So the EF minus the band gap. Okay, we reference to the top valence band. So I have the density of state in the valence band, density of state in the conduction band. Okay, and if we substitute EF, okay, EF down here in this equation of 2.3.15 into this equation, EF, okay, and EF of course involve emission and absorption of photon. So you have minus last okay. So the absorption coefficient will be proportional to the initial density of state multiplied by the final density of state, and then you integrate over all possible combination of state due to the emission or absorption of phonon. Now, for absorption coefficient, apart from the initial density of state and final density of state, you also have to include the so-called the number of phonon involved. And the number of phonon is basically the probability of phonon interacting with the electron. So the number of phonon is given by Bose-Einstein statistic. So for example, electron, you use Fermi-Dirac distribution. For phonon, you have to use the Bose-Einstein's distribution or Bose-Einstein statistics. So the number of phonon will be 1 over exponential term EP over KT minus 1. EP is the phonon energy, K is the Boltzmann constant, and T is the temperature. Now, these equations can be derived, okay, from statistical mechanics or also from the quantum mechanics, and we are not going into details. And this term is valid for the absorption of phonons. Now, so by taking the initial density of state multiplied by the final density of state, and then you integrate over all possible combination due to absorption or emission, okay, and then you multiply by a factor due to the phonon number due to Bose-Einstein statistics. So this n will involve temperature. So by integrating and substituting all the values, okay, of 2.3.19, okay, which involve the temperature, the number of phonon involved, you will get this term. So this term gives rise to the absorption coefficient due to the absorption of phonon energy. Now, for the phonon emission, okay, this term have to be plus 1, another term plus 1. Okay, this arises from the quantum mechanics. We are not going to the detail. So for phonon emission, okay, the probability of phonon emission or number of phonon involved will unique to NP plus 1, and that will give you this term. So the absorption coefficient for a transition with phonon emission, okay, by plugging in the NP plus 1 value, you will get this term for the emission of phonon for the absorption coefficient. So let us look at these two equations by plotting the graph. So the absorption coefficient should be the absorption coefficient due to absorption of phonon or the emission of phonon. So I take square root on both sides because the absorption of phonon, okay, for the absorption coefficient, if you take square root on both sides, this goes like a square, so it will be a linear term. Similarly, absorption coefficient due to emission of phonon, if you take square root on both sides, it will be a linear term, okay, since this is square. So there are two temperatures, so we plot square root alpha as a function of the photon energy. There are two curves. One is at low temperature T1, one is at high temperature T2, where T2 is greater than T1. So at the low temperature, you can see that the red curve is of this form. And in principle, you can take these two curves due to the absorption of phonon and due to the emission of phonon. So this part, you can see that the curve has kink and then it rises sharply, steeply. So this part is due to the absorption of phonon for the absorption coefficient, and this part is due to the emission of phonon for the absorption curve. So at low temperature, okay, imagine that at low temperature, your atom will have less freedom to vibrate. So the lattice vibration is very low because you need thermal energy, you need temperature, okay, for the lattice to be able to vibrate. So at low temperature, the lattice vibration is small. So expect the phonon energy to be small. If you look at the absorption curve for the absorption of phonon, imagine your temperature T is very small. Let's say tends to 0. So 1 over 0 is infinity. Infinity minus 1 is still infinity. 1 over infinity, your absorption coefficient due to absorption of phonon is very small, or tends to 0. But for the emission of phonon, okay, 1 over, let's say, 0 is infinity. E to the power minus infinity is 0. So it's a finite value. So it's easy to understand that at low temperature, lattice vibration is small because you need thermal energy for the lattice to vibrate. And therefore, when the electron traveling inside this in the periodic potential, you will interact with the lattice. You will get scattered by a lattice. And the probability of absorbing phonon energy from the lattice is small at low temperature because lattice is not vibrating vigorously. But that does not permit that the electron cannot emit energy. So electrons still can emit energy to the surrounding, even though absorbing the energy from the lattice is low. So the emission of phonon is still possible. So the absorption coefficient actually at low temperature, okay, is possible. So therefore you can see the absorption coefficient rise sharply by emitting of phonon. And for the absorption of phonon, okay, is low. So by extrapolating to absorption curve equals to 0, you can have two equations. So imagine you set absorption equals to 0. So this term multiplied by 0, you rearrange the term, okay, you would have the photon energy equals to, which is h bar omega equals to Eg plus Ep. Sorry, for the absorption of photon energy is this curve, you expect to have Eg minus Ep, okay, where the absorption equals 0. So the absorption equals 0, you have this term multiplied by 0 is 0. You bring the A over, 0 divided by A is still 0, okay, and then your h bar omega will be equals to, you bring the Eg minus Ep over, you'll get Eg minus Ep. Okay, so this point, h bar omega equals to Eg minus Ep. For the emission of photon, the same thing, 0 at the intercept, multiplied by this term is 0, divided by A is 0. So you bring Eg plus Ep over, your h bar omega should give you Eg plus Ep at the intercept. So at the intercept of the x-axis, where absorption equals 0, you have two equations. And you have two unknown. One is the indirect band gap of the semiconductor and the photon energy. Two equation, two unknown, but you know the value where it's intersect the photon energy, you can get the indirect band gap value of the semiconductor and also its photon energy. Now, let us look at the high temperature. At high temperature, so T is basically finite. Then the probability of the electron absorbing photon energy now is possible because your lattice is probably vibrating vigorously, so you can absorb the photon energy from a lattice. And then at the same time, the electron also can emit energy to the lattice. So if you plot the curve, in principle, you should. The blue one is a whole curve, but there's a kink here. And therefore, you can actually separate these two curves into absorption coefficient due to the absorption of photon and the absorption coefficient due to emission of photon. And it will be easier to plot as a square root of absorption curve because you take square root on both sides, then this is a square, so this is a linear term. Anyway, the numerator is just a constant because EP is a finite photon energy, and then KT is a finite temperature that you are measuring. Okay, let us look at absorption in germanium. So germanium is the indirect bandgap semiconductor. This is the top of valence band. So the reference is taken as energy equals 0. You plot energy as a function of K. So at the top of valence band is your gamma point. So the three component Kx, Ky, Kz is 0. Now, if you look at the conduction band, the minimum conduction band occur at the L value. Okay, at the L value. These are bottom conduction band, these are bottom conduction band, these are bottom conduction band, but the minimum conduction band occur at the L value, which does not occur at the same point as the top valence band. So this is an indirect band gap semiconductors. So the L point, you have Kx equals to 1, Ky equals to 1, Kz equals to 1. So by coming in with a photon energy, okay, you can have, let's say, absorbing a photon. So you excite to a virtual state, and then you can go to the minimum of conduction band. So this is a graph plotted, okay, as a square root of absorption as a function of photon energy measured at 300 Kelvin. So you can see that it's very similar to what we have discussed. This is the circle, the solid circle is the data point. So this is the curve of the absorption coefficient of the germanium measured at 300 K. So you can extrapolate down. This is due to the absorption of the phonon. This is due to the absorption, this is due to the emission of the phonon, and intersect at the x-axis. So you have two equations, and then you can calculate the band gap of the germanium and the phonon energy. So the band gap occur about 0.66 eV for the germanium, which is measured from here to here, from the top valence band to the minimum of the conduction band, 0.66 eV. Now, if we come in with a photon energy, there's another possibility that you can even have a direct transition, which means that I can have the transition from the top of valence band directly to this value. And that could occur, okay, also, if you look at this equation, this curve, the solid square, we go this way. Okay. Now, this is plotted as a alpha square. So down here, there's no signal. And then after that, it goes up linearly. So remember, in direct bandgap semiconductor, the absorption coefficient is proportional to the square root of h bar omega. If you take the alpha square, you take the square on both sides, and you plot as alpha square as a function of photon energy. So alpha square, it will be equal to h bar minus Eg. Okay, since you take the square root, so square will be h bar minus Eg. You expect a linear curve. So actually, you expect to have a linear curve. So the solid square, okay, this curve is actually due to a direct transition. Now, this is a direct transition in an indirect bandgap semiconductors. Okay? And at this point, okay, where it starts to rise, there's the onset of the absorption is about 0.82 eV. So if you measure from here to here, it gives you 0.82 eV. So absorption in indirect bandgap, not necessary, it goes from the top of valence band to the minimum of the conduction band, but it's also possible to have such a direct transition, okay, given sufficient energy to absorb from the top of valence band to here. So if you look at this curve, if I come in with a sufficient photon energy, I can absorb a photon by exciting the electron from the top valence band all the way to here, even though this is not the minimum of conduction band. So this is a direct transition in the indirect bandgap semiconductors. Let us look at the absorption in silicon. This is a band structure of silicon. Energy, again, is a function of K. Now, the minimum of the conduction band for silicon occurs somewhere around here, not exactly at the X value, At the x value, kx is 1, ky is 0, kz is 0. It occurs somewhere down here. Instead of kx equals to 1, is about 0.85. So similarly, you can come in with photon energy, okay, by absorbing a photon and you make a transition to here, to the minimal conduction band. That gives you the indirect band gap semiconductor. But it's also possible to have a direct transition, okay, for the from the valence band, okay, to the conduction band, and this is a direct transition. And there's another transition that can occur from the valence band to the conduction band. So in this graph is the absorption coefficient as a function of photon energy. So this part, okay, is the band gap energy that we are talking about, okay, by absorbing a photon. And then you have a E1 transition, which is due to the direct transition in the indirect band gap semiconductor in silicon. And then you can have also a E2 transition. Okay. So E1, okay, occur about 3.2 eV, and then E2 occur about 4.5 eV. Example 6, absorption coefficient of the indirect band gap semiconductor at liquid nitrogen temperature 77 K is given to you. Okay, so there's a constant part. If you look at the equation itself, okay, absorption is equals to this. So A is the constant. Okay. And then the band gap is given to you. Band gap is the one that is supposed to find, or we call the energy gap. Phonon energy is 0.04 eV. Okay. And given the photon energy 0.74 eV, the absorption coefficient is of this value, and the photon energy of 0.78 eV, the absorption coefficient of this value. Find the energy gap, or sometimes called the band gap of germanium at 77K. And what is the penetration depth for the photon energy? For H bar equals 0.8 eV. Now, we just need to take the ratio from this equation, and then you can cancel off the constant. Okay. So 0.2, you substitute the absorption coefficient for photon energy of 0.74, which is down here, and 0.2. Okay, band gap is supposed to find photon energy is at 0.04 eV. And then the other one, the absorption is 2, absorption coefficient is 2, the H bar omega photon energy is 7.8, okay, and the band gap is supposed to find, which is the same band gap as this, the same photon energy, 0.04 eV. So by taking the ratio, you can find the band gap of 0.683 eV, which is the band gap of germanium. And the penetration depth for a H bar omega 0.8. Now, you need to find the absorption coefficient for H bar omega, since absorption coefficient depends on photon energy. So again, you can take the ratio, but now since you know the photon energy and the band gap, it's easy to find the absorption coefficient, okay, at photon energy of 0.8. And that gives you the value of 3.56 cm per cm. The penetration depth, as we discussed in the early session, is equals to 1 over alpha. That gives you the value of 0.281 EV. If you look at the absorption coefficient, there's a factor of exponential to the EP over KT minus 1. So A over the EP minus KT minus 1, we take it as a constant term C, because that it will be at a finite temperature with the finite phonon energy. So A over the exponential term minus 1, this term, A divided by this term, will be the constant C, which is this C, okay, a constant term. For the next session, we will talk about absorption by carrier bound to shallow donor and acceptor. We will stop here and we'll carry on in the next session.